right, welcome to the fourth section of Chapter 7, where we're going to be talking about solving logarithmic equations and inequalities. So this is where we're going to go beyond just how to use them to what happens if they show up in an equation and how do we solve. So look out for the vocabulary of logarithmic equation and logarithmic inequality. There's going to be lots of different details you need to pay attention to in this section that will help you distinguish, because we're going to learn several different ways to solve logarithmic equations and inequalities. So make sure you're paying attention to the details and the differences between each kind of equation. So a logarithmic equation contains one or more logarithms. Amazing, right? So you can use the definition of a logarithm. Remember we said, for example, that log base 3 of 9 equals 2. We could rewrite that as 3 squared equals 9. So sometimes I can go from logarithmic form to exponential form to help me solve a logarithmic equation. So for example, here I have log base 8 of x equals 4/3. Notice I have a logarithm on one side, no logarithm on the other side. Okay, so that's the kind of equation we're looking at here. A logarithm on one side and not on the other side. So this is my original equation, and we're going to use the definition of a logarithm to rewrite it in exponential form. So 8 to the 4/3 is equal to x. So I rewrote it. Now my logarithm is gone, and now I can just solve this like normal. 8 to the 4/3, remember that's 2 cubed to the 4/3, or another way to rewrite this, if you prefer the radicals, is the cube root of 8 to the 4th. Right? So either way, you end up with 2 to the 4th, which is 16. So in this case, we get x equals 16. All right, so I want you guys to try this one. Log base 27 of n equals 2/3. All right, your answer should be C, which is 9. And there's the work. Just like in the last example, I showed you both ways. I can either rewrite it as a radical, or I can rewrite this as 3 cubed to the 2/3. 3 times 2/3 is 2, and we can simplify from there. Okay? So what we're going to look at now is what happens when I have a logarithm on both sides of an equation. So notice here I have log base b of x equals log base b of y. There's one logarithm on both sides, and they both have the same base of b. That can only be true, those can only be equal to each other if x, what's inside the log here, is the same as the logarithm here. So one logarithm on each side, same base of the logarithm, they're equal, can only be the same if what's inside here is the same as inside here. So if log base 5 of x equals log base 5 of 8, then x has to be 8. Right? That's the only way those could be equal, because I have a single logarithm on both sides with a base of 5. So if we take a look at this, log base 4 of x squared equals log base 4 of negative 6x minus 8. So again, one logarithm with the same base 4 on both sides. This can only be true if x squared, what's inside the logarithm on the left-hand side, is equal to negative 6x plus 8, what's inside the logarithm on the right-hand side. So what's inside my logarithm here has to be equal to what's inside here, because I have a single logarithm on both sides with the same base. So here we're going to solve, since this is a quadratic equation, I'm going to get everything onto one side equal to 0, because notice I have an x squared term and an x term. And we're going to check and see how we can solve this. In this case, factoring works pretty well. Two numbers that multiply to 8 and add up to 6. That would be 2 times 4, 2 plus 4. And since my leading coefficient is 1, I know that my binomials have to be x plus 2 times x plus 4 equals 0. Since I factored and it's equal to 0, I use the zero product property, so x has to equal negative 2, or x could equal negative 4. But with a logarithmic equation, you should always check. It's really important to check, because remember that I'm not allowed to take the logarithm of a negative number, thinking back to the domain of logarithmic functions. So here we're going to check if x is equal to negative 4. I'm substituting into my original equation. So negative 4 quantity squared, that's log base 4 of 16. And on this side, I get negative 6 times negative 4, because negative 6x minus 8. and that gives me log base 4 of 16, so that works. Now I'm going to check x equals negative 2, and I end up with log base 4 of 4 equals log base 4 of 4. That's fine, because what I have inside my logarithm is the same, and they're positive numbers, right? So that one works as well. So both answers, negative 4 and negative 2, are correct. Okay, so this one is for you guys to try. Your answers here are 5 and negative 4. Here's the work for what that process would look like. Sorry, I got kind of both of my checks in different places. I didn't leave myself enough space, but both work here. Both 5 and negative 4 are solutions. All right, now we're going to talk about inequalities. A logarithmic inequality is just an inequality that involves logarithms. The following property can help us to solve logarithmic inequalities. So if b is greater than 1, remember b is the base of my logarithm, and x is greater than 0, because I cannot take a logarithm of a negative number, right? My domain is x is greater than 0. If log base b of x is greater than y, right? So if this is true, then x is greater than b to the y. Be careful with this because it matters which side you put the x on and which side you put b to the y on. The x, this part right here, has to stay on the left, and b to the y has to go over here in order to maintain that x is greater. When it's an equal sign, it doesn't matter, b to the y equals x, x equals b to the y. But when it's an inequality, this order is super important. Now, with the same stipulations, b is greater than 1 and x is greater than 0. If log base b of x is less than y, then x is less than b to the y, but notice we also have to put this in here, right? If I just put x is less than b to the y, then x could be a negative number. And remember, we are not allowed to take a logarithm of a negative number. This cannot be negative. So we have to put in this extra stipulation here that it also has to be greater than 0. So x has to be between 0 and b to the y. So let's try this one. Log base 6 of x is greater than 3. This is greater than, so we don't have to worry about the 0. I'm just going to rewrite it using the property that we just looked at on the last slide. My x stays on the left, is greater than 6 cubed, greater than 216. Easy peasy. So my solution is the set of x such that x is greater than 216. So here's one for you to try. All right, your answer here should be B. And there were a couple things you should have noticed. This is a less than inequality, not greater than, so I do have to worry about the 0. So x has to be less than 3 squared using the definition of a logarithm, but also greater than 0. So x has to be between 0 and 3 squared, meaning that x has to be between 0 and 9. All right, let's take a look at this next property for logarithmic functions, a property of inequality. If b is greater than 1, so again, my base is greater than 1, then log base b of x is greater than log base b of y if and only if x is greater than y. So this works really similarly to the equation one. The only way this side can be greater than this side, if I have one logarithm and the bases are the same, right, these are both base b, is if what's inside this one is greater than what's inside this one. And it works the same way for less than. Notice I have a logarithm on both sides with the same base. This is different from the ones we just did. The ones we just did had a logarithm on one side and a number on the other. These have a logarithm on both sides. So if this logarithm is less than this logarithm, what's inside of them, since both of the logarithms have the same base, has to maintain that less than relationship. X has to be less than y. So if log base 6 of x is greater than log base 6 of 35, x, what's inside this logarithm, has to be greater than 35. So if we take a look at that in this situation, log base 7 of the quantity 2x plus 8 is greater than log base 7 of the quantity x plus 5. That inequality relationship, because I have one logarithm base 7 on both sides, my inequality relationship has to be maintained. So 2x plus 8 has to be greater than x plus 5. And then, of course, we solve. I would subtract 8 from both sides here, and I would get 2x is greater than x minus 3. And then we would subtract x from both sides. We get x is greater than negative 3. And that would be my solution set. And here is one more for you to try. All right, your solution here is a. X has to be greater than 4. And here's the work for that. If I subtract 5x from both sides, I get negative x. And then I subtract 5 from both sides and get negative 4. When I divide by my negative 1, I have to switch the direction of the inequality. You might have done it the other way and subtracted 1 from both sides and gotten 4 is less than x. But that's the same as x is greater than 4. So either way you decided to start should be fine. All right, that's the end of this section. So in class, we will be practicing these first few ways to solve logarithmic equations and inequalities.